In this video, we're going to implement a digital filter. Now, I'm assuming that we have a signal that we have run through an A to D converter. It's been sampled appropriately, and now we have it inside the computer, and now we want to do some signal processing on that signal. The most common thing to do, of course, is to filter it, and we have to figure out how to actually implement a digital filter. Implementation here, of course, means software. And we have many things we can do in software. You can do essentially anything you want, but we need something that will wind up giving us a linear shift invariant filter. And the technique I'm going to talk about today is the difference equation approach. This is a quite general approach and allow us to have any kind of filter we want: low pass, high pass, band pass. We're going to talk, though, about some filter categories that come up in the digital world that this kind of categorization doesn't come up in analog filters at all. So it turns out to be very important for the digital filters to understand these categories. And we're going to develop new input-output relationships, both in the time domain and in the frequency domain. And we'll see how that works. Well, first of all, we have to define what a difference equation is. So we have, for example, what we want to do is to implement a linear shift invariant system. And as always, we're going to let X be our input and Y will be our output. And the big question is going to be, how do you actually build filters? How do you implement them for digital signals? Don't have circuits anymore. You're inside the computer. It's all done in software. So the technique we're going to use is one called the difference equation. And the difference equation is quite simple. We have here the output, and we can see that the output depends on previous outputs, the one just before it and the one that was P samples away. You multiply them by these constants and you add them all up. Then you take the current input, the previous input, going Q back in time, multiply them by their own constants, add them up, take the sum of all that, and that is your current output. So the output now equals the previous output times A1 plus the one P times ago times AP plus B0 times the current input, etc. So you can see it's a pretty simple thing, and it turns out we will only need to know these what are known as filter coefficients, the A's and the B's, and how many of them there are. That's the P and Q. Once we have those and all the filter coefficients, we can do anything we want. Literally, you can do some very fancy filters, even ones that go beyond band pass, low pass, high pass, that kind of thing. Now, I want to point out that this is an explicit input-output formula. What I mean by that, not only does this equation, the difference equation, specify the kind of filter we want through its coefficients, but this is the way you could implement it. You can actually program this up. You set up a table consisting of the previous Y's that you need, the previous X's that you have. A new input comes in, you stick it into this formula, multiply those things you stored in tables by constants. You've got the previous outputs, multiply them by their constants, add them all up, and now you've got the current output. For the next output value to compute, you put this over that place in the table, put this one over here, etc. Do the same thing to the X's, and you have now implemented a digital filter. You can actually, it's a very simple programming exercise, just consists of multiplies and additions, and turns out it's a very, very easy way to implement a wide variety of filters. All right, so let's see what the output is for a very simple filter here. for a very simple input. So I only have one previous output value that enters into the difference equation, just the previous one. And I'm just going to take the current input. So the current input gets multiplied by B, the previous output gets multiplied by A. Add those two things up, and you get the output of the filter. I do emphasize this is linear in a shift invariant system. The simple input I'm going to use is just a unit sample. So it's a very, very simple input. Only one value is not 0. We'll learn in this video that this is a very important input to know the output for. So what do we do? Well, what I like to do to point out how the difference equation works is to construct a table. So what I'm going to do is have the time index, the input value at that time, and the output value at that time, and we want to fill in the right-hand column of the table. And let's start at n equals -1. So we know that at this time the input is 0 because that's that value there. The question is now, what's y at -1? What the difference equation says is that that is equal to a of times y of n minus 2 plus b times x at -1. And we know that's 0. But what's y of -2? Well, that y of -2 from the difference equation, of course, depends on y of -3. And y of -3 depends on y of -4, going on and on and on back in time. Well, how do we get around this? Have these values been specified? And there is an assumption that we make in filtering, is that all signals at -infinity are 0. So with that, and the fact that the input is 0 for all these values back in negative time, we know that y of -2 is equal to 0. Well, that of course gives us that the output at time n equals -1 is 0. Well, now let's let that input come in, and now we're going to talk about what happens at n equals 0. We know that the input is a 1 there, and what we're going to do is to find y of n, we're going to multiply that by b, we're going to multiply that by a, add them up, and of course we get just b. And that also applies to the next value. We now, again, all we do is multiply that value by b and that value by a, add them up. That's exactly what the difference equation says to do. And of course, we just get a times b. And to go into the next moment in time and all succeeding ones, I think it's pretty clear that what happens, for example, at time 2, if we multiply that by b and that times a, we're just going to get ab squared. And it's, I think, pretty obvious that at any time n, as long as it's greater than or equal to 0, the output is b times a to the n. So when I put in a unit sample, my output is this signal for n positive. And I can write that very succinctly using the unit step in my notation here. So unit step, of course, is equal to 0 for all previous values, and then negative values, and then it's equal to 1 for values at n that are 0 or positive. And that's a very concise way of using this to write down this output. We're going to find this happens all the time, and it's very, very useful. Okay, so what does this output look like? So there it is, our difference equation, our input, and we have computed that for an output. Let's plot it for various values of a and b. Now, I think you can see that the coefficient b here amounts to a gain. If I change b, all that's going to do is make the signal bigger or smaller. So in all of these plots, I've set b equal to 1 to simplify things. And here's my favorite value for a filter coefficient, 1/2. And you can see the output of our filter here for this unit sample input is 1/2 to the n, and it just decays, and in fact it decays exponentially. If you have a equals minus 1/2, it's also decaying exponentially, but now the odd value samples alternate in sign. They're negative, the ones for the even ones are positive, and now you have something that goes up and down and has a very different character than when A is positive. And another interesting value here to play with is when A is greater than 1. And when you do that, the output here is going to be 1.1 to the nth, and it's going to grow. And this turns out to not be terribly useful. You think about it for a second. This part here, all these previous outputs when you're out in here are going to keep getting bigger and bigger and bigger and swamp out whatever values you had for the input, and basically the filter ignores the input when n gets big enough. So what we have is that we had better have the absolute value of A to be less than 1, or we don't have a filter that's interesting. It will, if you do use values of A outside that range, the unit sample response will just take off, and the filter has a mind of its own, as it were. Okay, so let's think about what this filter is. We know how to compute it, we can plot it, but what kind of filter is it? And that, of course, means we have to hop into the frequency domain. Well, to determine what the filter is, we're going to do exactly the same thing we did with analog circuits. I'm going to assume the input is a complex exponential at some frequency f having a complex amplitude of x. And we're going to assume that the output has the same form, complex exponential in, complex exponential out, and we're going to see if this assumption is correct by seeing if we can determine an output amplitude that will satisfy the difference equation. So I'm just going to stick in these assumptions for y and x, and what you get is something that looks like this. And notice this intermediate term in here, y of n minus 1. When you stick that in for the complex exponential, a factor of e to the minus j 2 pi f comes out, and you're left with our friendly complex exponential. And that's what I used when I wrote this equation. Well, I think you can see right away that what happens is the complex exponentials cancel, and sure enough, if I bring the ay term to the other side, factor out the y, and divide by 1 minus a, I have a solution for capital Y that works. As long as the ratio of y and x is equal to this, if I stick in a complex exponential, I get out a complex exponential. Well, we call this ratio a transfer function. So we have used this technique to find that the transfer function has this form. Well, as we've seen already before, the b here just amounts to a gain for our simple filter. So whatever number you put there just supplies a gain for the transfer function. For the filtering, though, is affected by A. What kind of filter it is, how good a filter it is all determined by A, because that's where the terms involving frequency are. All right, so what we've seen is that the output is equal to the transfer function times the complex amplitude of the input times the complex exponential. Complex exponential in, complex exponential out. Well, what does this transfer function look like? So here are some plots, and for various values of a, and again, just like I did before, I set b equal to 1 because that's just a game. We don't need to worry about it too much. Okay, so for my favorite filter value here, an a of a half, you can see that it starts out and kind of gets small. So I guess you'd call that a low-pass filter. It's not a very good one. And what are these values here at the low and high frequencies here? At f equals 0, you put in f equals 0 into this formula, you get 1 over 1 minus a. Stick in f equals 1/2. Well, e to the minus j 2 pi f times a half, well, that's e to the minus j pi, and if you know that's minus 1, and so it would be good for the value at frequency a half is 1 over 1 plus a. So this value is something like 2/3, and this value up here is 2. So it doesn't have much difference in the gain at high and low frequencies. However, if you stick in a bigger value, a like 0.9, remember we have to keep the values of a in magnitude between 0 and 1. So a is a pretty big value for a, and you can see we get a much nicer filter, and it is low pass. So what we have found out here is that for a positive, that implies low pass filtering. So if you now think about the negative values of a, you get a high pass filter. And if I use a value of a that's minus 0.9, then we get something that's symmetric and gives us a very nice high pass filter. So a greater than 0 but less than 1, I get a low pass filter. If I have an a less than 0 but greater than minus 1, I get a high pass filter. Okay, so what happens in general? How do we find the transfer function for a difference equation in general? And you do exactly what we've just gone through. Set x equal to a complex exponential and assume that the output is the same. And I think it's pretty easy to see. It's all going to work. And what you get for a transfer function always looks like the following. You have a numerator term which consists of the input terms from the difference equation. You're going to have a denominator that consists of all the terms that involve the previous outputs. The coefficients of the filter are staring you in the face from the difference equation. Very, very easy to write this down. That's not very difficult at all. I do note that this minus signs come about because of the way you have to solve things. Remember, we have to bring these terms to the other side when we found the transfer function. So the b's all come in with plus signs, the a's enter downstairs with minus sign, and this we can use to do what's called filter design. So what you want is a way of choosing these filter coefficients a and b in such a way that you get the kind of filter you want. Where there are software packages that do this. It's not nearly as hard as it might be in the analog world if you're stuck with circuits. You can use software packages and they will, you tell them what kind of filter, you tell the program what kind of filter you want, low pass, let's say, cutoff frequency of 0.2, and you specify how good a filter it is, how sharply it goes to 0.2, and it will pop out the filter coefficients that you need. It's not very hard at all. Well, let me point out something that is different than the analog world. And this is a special filter, special kind of filter, and what makes it special is that there's no term here that talks about the previous outputs. That's right. So this filter, the difference equation, only depends on the input. And we want to figure out how this works. Well, I'm going to do the same thing I did before. I'm going to assume I have a unit sample input, and I'm going to build my table. Well, it turns out to be a whole lot easier than it was before, since this output here only depends on the previous inputs. There's no concern about what y of minus 2 is. So we're sitting here at time n minus 1. What this filter does is it takes together all the input values here, adds them up, divides by the number of terms, and puts out the answer. Well, of course, that's 0. Well, if we now encompass that unit sample, we look here, we go back, q terms, add them all up, divide by q. Well, it's pretty clear that you get 1 over q. And if you go to time 2, we're now right here. So what the filter does is it takes that value and the q one's previous, adds them up, divide by q. Well, we're only getting this unit sample in here. Everything else is 0, so again we get 1 over q. And we can keep going with this. I think it's pretty clear. We still get answer 1 over q until we get to the time q minus 1. And that turns out to be right here. So if you look at this last term, corresponds to this, x of q minus 1 minus q plus 1. Well, that's x of 0. So this is going to be the last time in which our filter grabs the input at time n equals 0. And of course we get 1 over q for that. Well, beyond that point, the filter is sitting out there, and it grabs only these inputs, adds those up. They're all 0, so you get 0. So for all subsequent times, the output is just 0. So for our special filter, which has this difference equation, we put in the unit sample. The output basically looks like a pulse, and that's what it is. It's a pulse. So here I plot it for a specific value of q, and pretty easy to implement and see what's going on. Now, let me point out something about this filter that makes it special. What is this filter doing? It's taking q values of the input, adding them up, and dividing by q, the number of terms. What would you call that in standard non-technical parlance? You take q values together, add them up, divide by the number of terms. Well, that's called averaging. So this filter is special in the sense that it averages its input over q values, and that's what the output is. Sometimes this is called running average because you keep doing this every n, and whichever n you pick, you're averaging over this, then you're averaging over that, then you're averaging over that, etc. Well, what kind of filter is the averager? Remember, we want to implement our in software our filter with a difference equation. But what kind of filter is it? Well, what I'm going to do is find that transfer function. And remember, the general form is that when you only have the inputs, what you do is you're going to get a transfer function that just has that in the numerator. So for the transfer function here is going to be, so we're going to get a 1 over q times 1 plus e to the minus j 2 pi f plus e to the minus j 2 pi f times q minus 1. And all the filter coefficients are 1 over q. Well, we've seen this sum before. And that should remind you of the digital sync. And there it is. So there's our digital sync. There's the 1 over Q. And we get this linear phase term that we know comes from adding up all these terms. Well, what does that look like? And what we see is that our averager is a low-pass filter. This is a very important concept to have. Averager is equivalent to low-pass filter. The cutoff frequency, if you will, is at 1 over Q. This is a plot for Q equals 5. And so if I come up with a filter with a bigger value of Q, I average more terms. The gain at the origin is still 1, but the cutoff frequency is down here, and the ripples get smaller, actually. So you can have a better low-pass filter by averaging more terms, but also the cutoff frequency moves to lower frequencies. Well, I think intuitively this is exactly what averaging does. It removes high frequencies and leaves only low frequency variations. And I think it makes intuitive sense that averaging could be just a low-pass filter. And I think it's very neat that in electrical engineering we can actually implement averaging and think about it as a filter, especially on a computer. Well, I now want to do something special and point out why the unit sample response is so important. So here's our linear shift invariant system, and it turns out I'm not going to worry about whether it's implemented with a difference equation or not. It's just linear and shift invariant. What I want to do is, for an input, I want to use a unit sample. And I'm going to refer to the output for that special input as little h of n. So in notation, little concise notation, if the input signal is a unit sample, we're going to call that special output little h of n. Okay? Now, because this filter is shift invariant, if I delay that unit sample by n at the input, the output is just going to be a delayed version of the output little h. Okay? Very important fact to realize for what's coming up. Well, as we've seen, you can think about every signal in discrete time as a superposition of unit samples. So the unit sample at the origin and its amplitude is x of 0. Unit sample at time 1, its amplitude is x of 1. Here's x of minus 2. And that's just a unit sample at time what am I saying minus here? It should be plus. So unit sample, this is a unit sample whose amplitude is x of plus 2. X of plus 1. And I can write that concisely. That expresses the superposition. Well, if I stick a superposition of signals into a linear shift invariant system, what do I get out? I get a superposition of the outputs to each. And therefore, we can immediately write that the output for our input x, expressed as a superposition of unit samples, is given by a superposition of delayed unit sample responses. That's what little h is. It's called a unit sample response. Well, in fact, we now have a very general way of expressing the input-output relationship for a linear system. You give me the input signal, you give me the unit sample response. I can use this sum to compute what the output is. You don't need the difference equation. This is an alternative. It's usually not a efficient way of computing the output. The difference equation is much, much, much better. But for theoretical reasons, as you're about to see, this is an important input-output relationship. Well, I want to find the transfer function, because it should be, as we've seen, for a linear shift invariant system, we should be able to find the Fourier transform of the output is related to the Fourier transform of the input. And toward that end, I'm going to compute the dTft of the output, which means I take the output signal, multiply it by a complex exponential, add them up. I do the same thing to the other side, and what I've done is, since I'm summing over n here, I've moved that sum on n inside and do it first, because there's only one term that depends on n. Well, what's this? What is that? That, to me, looks like the dTft of a delayed signal. And so I know what that is. That's the same as the dTft of little h times a linear phase. Well, what do you call the dTft of little h? You call it big H. So I think you see where this is going and how we're going to get to the transfer function. There's what we're going to call the transfer function in just a second. And so there's the linear phase that has to do with that delay. If I pull this term out of the sum on m, doesn't depend on m, I now see I've got the dTft of the input. And I arrive at a very nice result, that the dTft of the output equals the dTft of the input times the transfer function. But what the new thing is here is that this is the Fourier transform of the unit sample response. So transfer function here, unit sample response here, and they are constitute a Fourier transform pair. So this is a way of finding the transfer function. That's why finding the unit sample response and all those examples we did for difference equations was so important. It's because I know that if I can compute the dTft of that unit sample response, I've got the transfer function right away. Very, very nice. Well, let's talk about those filter categories I mentioned. We like to think about digital filters as falling into one of two classes, the FIR and IIR. And what does these acronyms mean? Well, it turns out the FIR case, it turns out means finite. There's a word missing in the acronym, duration, impulse response. That's what FIR stands for. And the impulse is another name for a unit sample. So to keep things short, this has been adopted since the beginning of digital signal processing. And so what that means, as we've seen, is that the difference equation has no terms that depend on previous outputs. Only consist of terms that add together previous input values. When you have a difference equation that's a little bit more general, that includes those output values in addition to the input values, we know that the unit sample response, as we've seen in our example, is infinitely long. Remember, when we had one term, our unit sample response what looked like a to the n, which lasted forever. Even though the unit sample, which is only one sample long, the output lasts forever. So that's what IR stands for. It stands for infinite duration impulse response. So these categories depend entirely on the behavior of H. Well, so one little thing I want to do is compute the duration of the output for a finite duration input in the FIR case. This turns out to be really important. So let's assume that my input is something very simple. It's 3 samples long. Not very interesting, but will serve the purpose for this example. And my little h is something that's going down, looks like that, and then it's 0. Okay. Well, what's the output going to be? We know by the superposition principle that all we do is found the output for each of these inputs and then add them up. So the first one gives that for an output and goes to 0. The next one gives that for an output and then it goes to 0. And this one gives that for an output and then it goes to 0. And we add them up. Well, how long is this input? Is this output? The input went to time n minus 1. This thing goes to output q minus 1. Its duration is q. They're q non-zero values. And this time right here is n plus q minus 2. So that means it has duration n plus q minus 1. Duration of the output equals the duration of the input time plus the duration of the unit sample response q minus 1. So there's a little minus 1 here. It's sort of a bookkeeping kind of thing, but that's important to get this down, as you're going to see when we talk about this later. So back to the IIR case, if you have a finite duration input, the output has an infinite duration in general. So there's no real calculation to do there, but this is very important, as we'll see in another video. Well, another property of FIR filters is very important, has to do with the phase. You can have a linear phase, and we've seen that already for our averager, but in the IR case, it always has a nonlinear phase. And let me bring up the phase plots for our filters we've been talking about. So here's our linear phase coming out of an FIR averager. And what does linear phase mean? Linear phase means delay. So what this means when you have a transfer function with a linear phase is that every frequency may be filtered, its amplitude is changed, but every frequency, no matter what it is, experiences the same delay. When you have a nonlinear phase, if you're talking about a frequency here and a frequency here, well, for this one, it experiences that, but since it's nonlinear, these two frequencies experience different delays. Well, why is this important? This has to do with the subtleties in the way signals look. So it turns out your ear is very insensitive to phase. If you had the same filter implemented with an FIR filter or done with an IR filter, and you listen to the result, you couldn't tell them apart. You can phase shift the input, the speech input, music input, it doesn't really matter, as much as you want. With nonlinear phase, linear phase, you cannot with your ears tell the original from the phase shifted input. You just can't hear it. Your ear doesn't care. However, if you apply a nonlinear phase shift to an image and filter that, it will really mess it up. It will be entirely gibberish in most cases. So for image processing, they like to stick with FIR filters because you can design them to have linear phase in which everything just gets shifted over, but nonlinear phase for an image is very, very, very bad. And you'll see that as you take other courses in more advanced digital signal processing. Okay, so digital filters. Very interesting and very important classes of filters are described by difference equations. And not only is this a way of describing the filter, this is a way of implementing it. Now it turns out that the difference equation is not always the most efficient, and we're going to talk about this in another video. It's not the best way of implementing a digital filter. And what I mean by that is not as fast. Clearly you don't want to wait for your results to come in. You want your filter to run very quickly. Well, it turns out in terms of when you get into the details of counting the multiplications and additions it takes to find the output for a given input, it turns out the difference equation works fine, but it isn't the best. And we're going to talk about that in another video. So again, the input-output relationship for a general linear filter can be expressed at either the time domain or in the frequency domain. Time domain is this. Frequency domain is given by our old friend, the transfer function kind of relationship. And we can do either, specify what the filter does. Either way, I find using the transfer function is more useful when you're trying to figure out what kind of filter it is, for example. But the new thing is that the unit sample response and that transfer function are Fourier transform pairs. So if you can find this, you can find the transfer function very easily. It's not hard at all. You just find out with the DTFT. And in succeeding videos, we're going to talk about efficient ways of implementing filters. And it turns out many of those cases wind up being implementing filters in the frequency domain, kind of a non-obvious thing, and we'll talk about that coming up.